The first speaker will be Ines Aniceto, and she will tell us about special function solutions of Painlevé equations.
Tau.
Tau special.
Tau functions and special function solutions, yes. There's still special function solutions of Painlevé. So, well, thank you. Thank you for the invitation. It's like, as always, it's apart from the swimming, which is maybe you need to order less jellyfish for next year. But other than that, it's always a pleasure to come here, and I always have so many really nice discussions. Often not the discussions I thought I was going to have, but that's always better. So last year, I remember coming to talk about something that I thought, okay, I think it will appear eventually in physics, but I have no idea where or when or how. And as it happened, a couple of months later, I found out that it showed up in someone's work, because I came to talk about higher order Stokes phenomenon. So, it's nice to see that sometimes you talk about something that at that time is more mathematical, at least for this community, and then it actually shows up. So today, what I'm going to talk about is about the special function solutions of Painlevé. This is work with a mathematician, Alfredo Diagno. And so the main idea that I'm going to present, I'm going to give an introduction and what I want to do with it. And then I will try to tell you how these solutions can be constructed, because they actually can be constructed from classical special functions. And that's the neat ingredient in this. But one of the reasons that this project started was actually to understand how to go from asymptotics to something analytic in particular, and especially because this my collaborator is from the community of orthogonal polynomials. It was about talking how to find zeros of partition functions, of tau functions. And this is why we started. So this is what I'm hoping to get. So before that, so meaning what are special function solutions of Painlevé? So our solutions, so I'm going to do the one, and special function solutions of Painlevé, what they are, that's just that they can be written, as I said, in terms, like as a determinant, derivatives of the determinant of derivatives of a particular seed function, and that seed function is a well-known classical function. Special functions, and sorry, I can't even write special. And what are these special functions? We're talking about Airy, Bessel, parabolic cylinder functions, Whittaker, and hypergeometric functions. So where do they exist? They exist for Painlevé 2 to Painlevé 6. They're known to exist. And these depend on, meaning not for all of the possible classical special functions, meaning each one will basically choose one of the special functions. But they're known to exist for this, but it's not for any parameters of the Painlevé equations. It's for very specific parameters. And even for those, meaning it's not that if you tune to those parameters, the only solution you get is special function solutions. No, it's that for those parameters, special function solutions do exist. So why are they important? Well, they're important they appear in integrable systems, orthogonal polynomials, clearly. In particular, orthogonal polynomials, what you do, you grab the classical orthogonal polynomials, you deform the weights, you find, so the deform with the parameter t, you get recursion coefficients that depend on this parameter t, and these recursion coefficients are related to solutions of Painlevé equations, but because they can be written in terms of these determinants, you can actually show that there are special function solutions of Painlevé. Meaning also they show up in particular cases of random matrix theory. In particular, well, some classical ensembles. Clearly, most of the solutions that show up there are transcendent, but you also find specific solutions. There are special function solutions. So typically, if you get an n by n random matrix theory, if you take n to infinity, you don't get any special function solutions. But if you go to n finite, you do. And this is the situation. And one of the cases is that you can show that if you, like with gap probabilities, if you try to find the probability that there's no eigenvalue in a certain interval on the real line, you can actually show that, like for an n by n ensemble, you can show that the probability so basically let me just quickly write. So if I write that, like, so En is the probability of having zero eigenvalues from, for example, S to infinity, basically this is like a tau n, and tau n being specifically a tau function of Painlevé 4. And you can show that this tau n actually obeys a Toda type equation. So you can create the extra tau n's from the previous ones. And n is so you try the Gaussian unitary ensemble, n by n.
So this is the residuum.
Yeah, exactly. That's exactly that. But this is just motivation. Sorry, there's nothing. Exactly that. It's exactly that.
You have something also for Painlevé 2, which is probably the simplest.
So that's the one that I'm going to mostly show, although I'm going to write it. So, meaning what I'm going to write actually works for pretty much any of them. So Painlevé 2 has Airy, which is, yeah, indeed, the simplest one. But all of them, in any case, obey second-order linear ODEs, the seed functions, and that means that they have all the same type of structure, generally speaking. This is one. So another thing that I leave to the audience is clearly, meaning what I'm going to present, meaning is not about Painlevé transcendence. The similar things can be done for Painlevé transcendence. I've done that for Painlevé 1. At least the truncated solutions, but the one question is like, what are these tau n's in terms of from the physics point of view, right? So it's very easy, meaning people will tell me, oh, what tau 1 is, but I would like to understand better the tau n in particular. I think I mentioned this last year, and someone said about some particular masses, but I would like to see that more concretely. So what am I going to do now? I'm basically going to use the Hamiltonian formulation of the Painlevé equations and basically the related tau functions, and basically state that for special values of the parameters, these tau functions can be written in terms of Wronskian determinants. And Wronskian determinants constructed from a single special function. So basically, I'm going to use this and choose special values. I will mention what they are of parameters. And basically, that means that my tau n's are going to be a Wronskian of some phi. Let's write phi of z, where phi of z is a specific solution. So when I mean a specific solution of the classical special function, I mean that it's not a specific solution, it's a combination. So it obeys a second order linear ODE. That means when I'm talking about ARI, I'm not going to say that it's a combination of AI and BI. Instead, I'm going to use the asymptotic expansions, so that I can try and see how that relates to the full tau ends. And basically what will happen is that these tau ends of Z obey a Toda type for these special functions, Toda type equations in Z. And that is what I will really use. And these can be obtained by Backlund transformations. So making use of the integrability of the.
I never seen inverse scattering applied to Painlevé equations.
No, but isn't it equivalent to using Backlund transformations generally?
No. In fact, it's a fundamental theory based on another fundamental theory due to Van Faddeir, which is the inverse scattering, classical inverse scattering was by the Chicago school. Anyway, we can talk about that.
So we know that Painlevé equations can be written as in a Hamiltonian system. So we have a pair of conjugate variables, and we have dq dz equals to some Hamiltonian. So the q and p are conjugate variables. dp dz equals to minus dh dq. And basically h is the Hamiltonian. So when I write h of z, q, p, and then it will depend on some parameters, some vector of parameters v in general. And basically what happens is that then if I can't calculate q of z will give you the Painlevé equation, will obey the Painlevé equation. So then, and as usual as well, I can define a tau function, which is just the ddz of log tau. So the Hamiltonian is ddz of log tau. Clearly depends on v. And then what you do is like you start with some initial set of parameters v. So you can start with some initial set of parameters v, and then you can apply Backlund transformations over and over and over. Basically, you say that you have, you say that T is like the Backlund transformation. Sorry. So, and basically what I'm saying is like if I apply Tn to the Hamiltonian that started with my V0, what I will get is the Hamiltonian. So it relates the space of solutions to the space of solutions, but with different parameters, right? So the idea is that then what I get is the Hamiltonian at V0 plus n some V. And this is equal to the d tau of log of tau of now that depends V0 plus n V. And that's the new tau n.
So you're saying that, for example, if I have an equation which has more than one parameter, I just choose to transform one parameter. So, for example, for Painlevé 3, I will just transform one of them and apply always the same Backlund transformation.
You would apply you'd apply always the same Backlund transformation. Because like it's a very specific choice of parameters that allows you to do this. You get still one free n, but it's one very specific choice of parameters.
derivative with respect to z.
The z, sorry. You were right not to understand it. And moreover, these obey a differential equation where d is a order 1 differential operator. So let me just take this tau n. d2, it's given by t n plus 1, tau n minus 1 divided tau n squared. And this equation is actually the equation that we'll make a lot of use of. For meaning, and where tau 0 is given by some initial data. So another thing to mention that I'd like to mention is that these tau n's can be shown. So the tau n's can be written, as I mentioned, by a Wronskian determinant, which is basically the determinant of this operator I plus j of a seed function where I, j go from 0 to n minus 1. And this is for n greater or equal than 1. Tau 0, again, is a special result. So this is the...
So this is for the class, for the Okamoto solutions.
Many, these are all the special function solutions.
Not the algebraic ones.
Not? Yes. So typically, clearly, what happens is like I have a tau 0, tau 1 is just the original pi. So now I have a big table, but perhaps I will choose. So Painlevé 2, you have, meaning again, Painlevé 2 has the seed function is the Airy solution. Painlevé 3 is the Bessel. Painlevé 4 is Hermite, Weber-Hermite. Painlevé 5, Whittaker. Painlevé 6, hypergeometric. So this is the different cases. Operators, for example, so let me write just Painlevé 2 and let me write Painlevé, doesn't matter, 6, just so that you see examples. So the seed function is Airy. Here it's Gauss hypergeometric. Here the operator is ddz, just a simple operator. Here is z minus 1 ddz. So this is the type of operators you find. There's a few are ddz only. There's another one that is z ddz. This is as complicated as it gets. And then here, for example, the parameter is like, if you look at the parameters in DLMF, alpha is equal to n plus a half. And here you have like some a plus b plus c plus d equals 2n plus 3, where I'm going to write just, so a is just some square root, some epsilon 1 square root of 2 alpha, b equals epsilon 2 square root of minus 2 beta, and alpha beta. So there's a few more. Again, all of this is listed in the LMF. There's a c is epsilon 3, 2 delta, 2 gamma, and d is epsilon 4, 1 minus 2 delta. The epsilons are just plus minus 1 independently. You can choose one. So, but you have something like that. So specifically, this is the parameters. The parameters have to obey this. Again, the parameters obeying this doesn't mean that you have a special function solution. It means that they need to obey this to have a special function solution. So, and with this, I would like to write what is the goal before I go into the actual calculation. So the goal is basically we consider the large Z asymptotics of the seed function And this one is well known, meaning the large-headed asymptotics, the Stokes phenomena of the seed function is extremely well known. Meaning this is talking about airy functions, hypergeometric functions. They're very well known. And what you do is that you do that. You determine the asymptotic. And by the way, when I'm talking about asymptotic behavior, I'm not talking about just the leading term. I want to really calculate the full structure when z goes to infinity. Behavior of the tau n functions for general n. So the idea is that I want this for general n. And then, so this, what does this include, this asymptotic behavior? It can include just regular power series, the Poincaré asymptotics. It can include exponentials. It will include exponentials, and it will include logarithms. So it includes all of the usual. So this is going to be put into what is called a trans series with all of these elements. And then what I want is actually to determine, use this to determine analytic approximations for the zeros of the tau n's. So I want to determine the analytic approximations. And analytic, I mean asymptotic approximations. So also it has an asymptotic structure, and I can calculate the position of the zeros from that structure. So this is the idea. Why would an asymptotic behavior give me access to the zeros of the tau functions? Well, it gives us access to that because generally, again, the zeros are in situations where the exponentials that will show up in that full solution compete with each other. And when they compete with each other, you actually have access to zeros. And what you'll find is that we'll go to regions where we still have our asymptotic parameter z, but the exponential is not going to be small anymore. It can be of order 1. The exponentials can compete.
Because in some sense, I'm a little bit surprised because I thought for this solution, special function solutions of Okamoto, you can actually write down the solution of the Painlevé equation explicitly.
The Riccati solution you can.
Yes. No, you can write the solution to the Painlevé equation explicitly. For Okamoto, for this Okamoto, you can write.
Not for these general special, not for the tau n. So typically you can, yeah, for the tau n's, no. For tau 1, you can.
This is amazing. I didn't know. Okay. No, I find it incredible because in some sense, we know the solution of the Painlevé equation explicitly. And then you're telling me that if I try to compute the tau n, I'm still in trouble. That's amazing. Okay.
No, this is asymptotic behavior in n, which is what
Yes. But somehow I thought that I understand.
No, but one thing is having the explicit formula, and another thing is having the solution in Z, right? So you can write it, meaning that's the solution. If you want to say it like that, that's the solution. You have the solution, but it's a difference from writing that to writing what the asymptotic solution in Z, or to be able to do anything with the actual. So there are integral representations for some of them as well, for example, that have been studied. Meaning they clearly come from random matrix theory, for example. So again, I think I think there was a misunderstanding when I think about actually the solutions are not known. It means that for me, meaning if I want to write the asymptotic behavior of the solutions.
But when you say solution, are you talking solution of the Painlevé equation or the tau function?
The tau function.
Because what I'm saying is that the solution to the Painlevé equation is
to the Painlevé.
Okay, that is explicit. But so that's why I'm asking. So there is something going on with tau function, obviously.
No, but for example, look at Painlevé 2. Sorry, and I should check the time. Meaning what we're writing is a solution that is where the parameter is n. So there's a particular case for n equal when I wrote there n equals 0 where you have a solution of the Riccati equation. That's very easy to write.
Background and write explicitly if you want, but
for any n.
No.
Exactly, but that's what I mean. That you have the explicit solution, meaning this is what you get from this. You have the solution. You can apply background transformations and calculate if you want, but you don't have a closed form expression for general n.
Just to make sure, the last thing you said, I want to understand. So you want to find zeros of tau n. This is a Wronskian, so you say Wronskian will vanish determined by what is the leading asymptotics of the solution. Is that all?
I will not. No, you don't need the leading. So when you do asymptotics in a region, you typically the leading asymptotics doesn't include the exponentials, which can be small, and you need all of the exponentials to find the zeros. So you need to go quite beyond what we would call leading asymptotics to actually find zeros, or you need to find, well, what would like instanton contributions. But yes, that's what I want to do. So now, let's go to the construction of the thing. So what I'm going to write here is generic for any of the Painlevé equations. Of course, there'll be quirks on each one of them that need to be taken care of, but the general picture is all the same. So we start with the seed function, which I'll write as phi of z equals going to be some constant phi sigma 1 e to the minus f of z phi 1 plus sigma 2 e to the f of z phi 2. So sigma 1 and sigma 2 are constants. Phi 1 and phi 2, I'm assuming that they're asymptotic expansions for z large. In some specific, and I'm assuming that we're in some specific Stokes sector. So the first thing you do is that you can change variables. So all of them will be of this shape, but we can change variables where we say that f of z is going to be some a over 2 x. And think of this as f of z. This can be, z to the 3/2, like
So phi 1 and phi 2 are the solutions of the linear special function. So
phi 1 and phi 2 are exactly airy. But I am using, but I'm not using the actual, so the reason why I'm not using the actual airy and Berry is because those, if I talk about those specifically, I'm talking about those with the Stokes phenomenon associated to those. Here, I'm saying I'm dealing with the Stokes phenomena myself. I know how these asymptotic expansions jump, and the sigmas will jump when I cross, and I know they jump by I, for example, for the airy. So I don't want the Stokes phenomena to be hidden within the AI and the BI. I want to make it explicit. That's the only reason. You can do this with AI and BI. Actually, it took us a year to find a factor of 1/2 in our work because of that. Because I was working with the asymptotic expansions, my collaborator was working with with airy and Berry, and that really led to a lot of confusion. But anyways, the point is we want to make it explicit because this parameter sigma actually do have a role in the zeros. And now it's 1/2 hour, right? Yep. So think of this change of variables like so. Here, usually it doesn't show up as z, shows up as a power of z, but it's much easier to deal with the simple variable x, where the Stokes phenomena happens at 0 and pi, and there's nothing else. And then we can always go back to the original. And of course, I could always choose this part to be 1, but typically in a lot of the asymptotics of these classical special functions, it's not. It's some value. For example, A is 4/3 for Airy. So it's better to use the expansions that are well known. So that's why I included the A. So A is greater than 0. And so then I write now phi of x, which is again sigma 1, e to the minus a over 2x, phi 1, plus sigma 2, e to the a over 2x, phi 2. And I'm still saying, yeah, that x is large in this case. So what are the phi's? The phi's, I'm assuming that they typically have some behavior like this. So they have, this is an algebraic factor, overall algebraic factor. There's no expansion in x here. And then there's a whole expansion j greater or equal than 0 of phi ij. These are just coefficients x to the j. So this is what it'll look like. Meaning this, I haven't done anything. This is just special functions. I can always do this to the special functions. Again, I just stress that the sigma 1 and sigma 2, you define them in some particular boundary, but then Stokes' phenomena tells you what they are everywhere in the complex plane. So what we do now is that we can use the known special function asymptotics, and the tau function now inherits this asymptotic description. Actually inherits all the asymptotics from the seed function. There's nothing new. All of the asymptotics of the tau function is coming from the asymptotics of the seed function. And you can prove that, so for the tau function, you can use the determinant formula, Hankel determinants, and you can prove that tau n of x will be some algebraic factor overall, and then it will be some r equals 0 to n, b n r of x and let me just write what fn. So fn is just an algebraic factor which is a constant, and typically like some x to some alpha n to some thing, and then that bnr goes as x to the r n minus r some k. This is a k, a r k n, and this is when x goes to infinity. One thing, if you ever seen a trans series for Painlevé, one thing that you might notice directly is that there's a finite number of exponentials. So if you did, and the construction actually passes through calculating the free energies, meaning the logs of the tau functions, and those have an infinite number of exponentials. But when you exponentiate, you always get a finite number of exponentials. This is true for the special function solutions. So as soon as you have a transcendent, you have an infinite number of them. Of course, another thing we need is to have my operator D, which, because I'm going to use the, let me write it again. So there was the D squared log tau n, if I'm not mistaken. So yes, D squared log tau n is equal to tau n plus 1, tau n minus 1 divided by tau n squared. So that was the Toda-like equation. We need to write D squared clearly as a function. So if I wrote that if D was h of z, for Painlevé 6, this was z1 minus z. and there was a ddz, that means that this will be given by h of x dx dz ddx. So you write everything in terms of x, and then you apply it. So the question then is, can I write, and here I have tau 0 equals 1, it's just the identity, and tau 1 is my original seed function. So that's the initial conditions. So can I do this efficiently? Can I calculate the coefficients of tau n for any n in order so that I could do this for general n? And the answer is actually you can. You use this, but clearly because there's a log of tau showing up here, the best way to do the calculation itself is to go to log tau, just because it makes life simpler. In general, multiplying Trant series is a pain. Adding them is much easier. That's why. So it's natural to use gamma n, which is equal to log of tau n, which are the free energies. And what you get is that gamma n plus 1 is equal to 2 gamma n minus gamma n minus 1 plus log of the d2 of gamma n. And then clearly we have gamma 0 equals 0, gamma 1 equals log of phi. So what I would like to do now is actually to show you what the shape of the Trant series, so the shape of the full asymptotic series that we expect for both are. And so if I want to write asymptotic behavior, asymptotic Trant series, let's say, what I get for tau n, and I'm going to write it now in a slightly different way than I've wrote it before. I can write it like this, NA over 2x. And you'll find it perhaps that it's a bit strange to write it like this, but I'll make it clear in a second. Sum r equals 0 to n this is the tau n, where the zeta n is just sigma xn e to the minus ax. And also sigma, I didn't mention, I should mention here, at the moment I'm assuming sigma 1, sigma 2 to not be 0. You can do the same analysis if you start with sigma 2 equals 0, but for the calculations, it changes the asymptotic slightly, so it's slightly different. But so sigma is minus sigma 1 over sigma 2. Why am I writing the x here and then all the exponentials here instead of typically the other way around? Because when I calculate zeros, what am I interested in? I'm interested in a regime where x is still very large, but the exponentials are all of the same order, so that we have zeros. So I'm actually interested in calculating these objects here. And that's what will give me the approximations for the zeros. So I would like also to show you the gamma and just point out what is the difference between them. And the gamma n is equal log of fn, clearly, plus nax over 2, plus sum k equals to 0, meaning k greater or equal than 0, x minus k, sum r greater or equal than 0, psi r n r, and other coefficients. One thing that you already see, an infinite number of exponentials, not a finite number of them. And now psi n is not the same. It's very similar, but it's not the same. So it's almost the same, but not quite the same. But there's a big difference. So here I'm saying that these are the GKNs, and these only depend on psi n. And these, I'm going to call them the FKNs, and they only depend on this variable n. What's the other big difference between these two things is that if you look here, I have so x to the k is equal on the both, but here I don't have a power of x, there I have a power of x to the minus r squared, which means that it's a quadratic growth in the x. But as it happens, that makes the calculation of the zeros from that perspective much faster. So it gives you a much better approximation because you're calculating already a few contributions from x itself within the calculation. You could do the calculation of poles here as well, but it's just a slower calculation. I have some plots, but I think I won't do the plots because those even will take, just that will take some time. But basically the plots is just to show that there's this quadratic sum in there, like an evidence of quadratic sum versus here a linear sum. So what I would like now to do is to write, one thing is like, again, I deleted again, which is d squared. Do I have the one for gamma? Yes, I have the one for gamma there. So that's fine. That's the Tode equation written for gamma. Clearly, meaning if I want to calculate the g's, these g functions for the n plus 1, I need the g functions from the previous one. But the g function for the n plus 1 will depend on the psi of n plus 1, while the g functions of the previous ones will depend on the psi of the other ones. What does that mean? It means that we need to do something like realize that if I have g n minus 1 k of psi n minus 1, I need to write it as g n minus 1 k of x minus 1 psi n, and I expand for x small. And I get a series with the g of n minus 1 evaluated at 0. The derivatives of the g evaluated at 0. The thing is that I can calculate these g's exactly. And in fact, so if I give you, I'm not going to give you the coefficients. If you want me to give you the coefficients of the Airy function and all these functions for the Airy, I can. But what I would like to show you is just, if I do Painlevé Airy solutions, Painlevé 2, for example, G01 is equal to log of 1 minus psi. That's the type of functions you have. Actually, only the zeros have logs. The other ones are going to be like G1. 1 is equal to minus 5, 1 plus psi. So it's a rational function divided by 48 psi minus 1. And then the next one will have a double pole in psi. And then, for example, if I want to go to the G02, I get log of 1 minus 8 psi. If you look then to this one, it's going to be minus 5. I should have written it in a different way. 1 plus psi. Sorry, this is not. No, 17. Sorry. 17 divided, and this is not obvious. Sorry. I don't know why I wrote it like that. But this has the same meaning. It's a factor times the same exact pole. So this is a pole. The next one will be a double pole. And actually, meaning you can do this then very quickly. In Mathematica, we went to G15. So what do we do then? Well, we have this. Then we need to calculate the tau function. But the tau function is the exponential of this, and that will give you very quickly the results. The only difference you need to do is actually that you need to, for the tau function, you need to go to change psi n into x minus 1, like zeta n, and again do the exact same thing, exponentiate. So, and now tau n, you will get tau n, which is equal to the exponential of gamma n. If I write it as x minus 1 zeta n, and I just do the expansion, and I have my coefficients. So what did we obtain? We obtained a rk's n for k equals 0 to 4. And let me just write it again, tau n, because this is fn e to the n a over 2x sum k equals greater or equal than 0 x minus k. And then I have the f, what I wrote, fkn's of psi n. This is how the tau n's looked. What I'm telling you, if I'm telling you that I calculated these for any r and n, what I'm telling you is that I calculated 5 of these f's. And that, as I'm going to show you now, we're in business to calculate the zeros. So then, how do we go now to the final thing, which is the actual main motivation of this work, which was to calculate zeros? As I said, the zeros are 15? Yeah, that's absolutely fine. So what are how do we calculate the zeros? I need to write. So they, as I mentioned, they arise from a competition between the exponentials. So what I really want is to try and find, so I'm assuming that x is still large. So in this regime, I can say that, perhaps I can get a very good approximation at the beginning. But of course, what I would like is to set all of this to 0. But the first term is the leading term. So maybe I can first set that one to 0, calculate the position of the zeros, then see what the second one gives as a correction, and then a third one and a fourth one, etc. And that's exactly what you want to do. And that's why I'm saying that calculating 5 of those means that I don't only have the leading position of the zeros asymptotically, but I have also 5 corrections to it. So, so the regime that you're in is, I'm assuming that e to the minus ax is much greater than x minus 1, and that is still much greater than, sorry, what? No. And I'm saying that is still much greater than 1. So instead of the usual regime where we have the exponential is much smaller than the 1 over x, here I'm saying it's the other way. So I'm going to a region in the complex plane such that this exponential actually becomes, all of the exponentials become of the same order. So zeros will obey, f0. So the factor doesn't matter. So it's s0 plus x minus 1, f1 plus etc. equals to 0. But these are corrections. So I can start at least with f0 equals 0. And remember, f0, I'm going to write it again here, is sum r0 to n. And this is actually f0n. Sorry, I will omit the n. I'll write ar0. So it's k equals 0, n. And what I'm writing q is just x minus 1. It's just q is small, just for simplicity. And what I want is to solve f0 equals 0. And what I want to solve is that I want to assume that the zeta and the q are independent. So I'm going to solve one in terms of the other. So And I'm going to look for solutions that are of the type q minus beta sum k greater or equal than 0 dk q to the k for, at the moment, some beta. I don't know what beta is, but I'm going to look for a solution of this type. So we can do that. And what do you do? Well, what you really do is you plug this ansatz inside here, the f. Again, not inside the xi. The xi is assumed as an independent. Sorry, no, inside the xi, but you don't use the fact that you know what xi is in terms of x at the moment. That's a last moment inversion. So at the moment, you assume this ansatz here, and you expand it, and you see what you get. And what you get is that f0 is like some a00 plus q minus beta plus 1, and then you get to the d0 plus d1q plus etc. plus, sorry, minus, just writing the first few so that you see what, minus 2 beta plus 4, and then it's d0 plus d1q plus etc. squared. And the last one is like q minus n beta plus n squared with d0 plus d1q plus etc. to the power n. And I forgot here, this is a10, this is a20, and here it's an0. So this is the type of thing you have. Because I'm only assuming one correction, I'm only doing the f0, I can calculate for any of these d's, but the only ones that are going to be correct is actually the d0. To calculate the d1, I need to include f0 and f1, and then on. So you do that, and the first thing you say is like, okay, how can I have a 0 here? I can only have a 0 if beta has certain values. Meaning, depending on the beta, what will happen is that what you're going to have is like, clearly this has no q leading. What will happen typically with these betas is that you'll have a few positive ones, a few negative ones, reach a minimum, and then go to any other point because you have all these powers of q. And what happens is that you want those minima to cancel so that you can find a 0 always. And that you can find that beta has to be first integer, has to be positive, and you can clearly see that actually if beta is even, you will always have one single minima, so you can't. Minima of this, so what I'm saying is that the exponent is a function of beta, or a function of r, if you want, which is equal to r squared minus r beta. And this will have a minima. If beta is even, it will only have a single point, like one minima of the exponent. What you want is 2 so that they cancel. And then you can try and find solutions. So actually you find that beta has to be equal to 2m plus 1. And actually, because you have to have 2 minima, but the 2 minimum cannot be such that r is greater than n, because we know for a fact that r can only go to n. So actually you find that m is greater or equal than 1. Sorry, no, m is greater or equal than 0, beta has to be positive, and is less or equal than n minus 1. So so unlike Painlevé, that you have an infinite number of rays of zeros for the tau function, Painlevé 1, for example, transcendental solutions, what happens here is that you have a finite ray of zeros defined by n. And finally, you can do the calculation. You can calculate d0. You just solve the equations. You calculate d0. And you do one last step. This is the last bit. So I can tell you d0. This is, by the way, this is for Painlevé 2. d0 is minus 1 to the n, 2 to the minus 3n plus 3 2m plus 1, gamma n minus m divided by, not that this is not very obvious, but I'm writing it for a reason. So, and then the zeros you actually get from saying, but I know that psi n is actually equal to sigma x to the n e to the minus ax, and this is, I know that this is equal to x minus 2m plus 1, x minus beta, d0. Now I need to invert this. This is a Lambert W inversion, meaning you can solve this by expanding. You find, so this is a Lambert W inversion. I could show you how to do it, but I don't think I have the time. So, and you find that you have ax equals t plus n minus 2m minus 1 log t. These are exact. Anything else I calculate is not enough because I need more than the d0. And t is just log of d0 over sigma a n minus 2m minus 1 plus 2 pi I L, where L can be anything in Z. This gives me the towers, like the ray of zeros, and n gives you the number of rays. So why did I write these things? Because, of course, I need to remember that x and z are not the same. There's a change of variables. And one of the questions that are asked is, are there real zeros? Are there zeros that show up in the real line? And actually, you can see from this directly that there are. In particular situations, for example, if to have zeros, you have to have n odd. And this is something that has been seen. So, but you can only have zeros in these airy solutions if n is odd. And you can find that from this. So just to finish, so one thing that we'd like to do, compare with actual numerical predictions of the zeros for these special function solutions. And another question is, what do the zeros of tau n, what interpretation do they have beyond, random matrix theory, beyond zeros of orthogonal polynomials? And, well, thank you.
These are special functions. They're not polynomial tau functions. So no. What is the relation? Like, even just the idea with orthogonal polynomials. They're very ignorant question. I don't know.
So orthogonal polynomials, so actually you deform weights with a parameter, which means that then the recursion coefficients that you find from the orthogonal polynomials, these deformed orthogonal polynomials, are functions of the deformation parameter t. And those are solutions of Painlevé equations, special functions. I am not an expert. But it's something like that. So you have the classical orthogonal polynomials where you wouldn't have any of this, not directly. But you have a deformation of the weights inside the integrals where you define the measure. So the weights are deformed by a parameter, and then you find the recursion formulas. They're not, no. They're functions of t.
Yeah.
And it's in terms of that deformation parameter t that they're functions of, that they're related to. See, so you were, yeah? Very good. So I did write at some point, but I might have gone. So I said that I'm assuming sigma 2 is non-zero because sigma was minus sigma 1 over sigma 2. Sigma 2 still shows up in that Fn that when I wrote there was an overall factor. So that overall factor depends on sigma 2 as well. but because the overall factor does nothing to the zeros, it doesn't depend. But clearly, meaning so one other thing I didn't say is, like, if I want to find real zeros, depends on whether, so typically with the Airy function, the jumps are sigma 1, sigma 2 goes to sigma 2 plus I sigma 1. So this sigma, you can imagine it being I, which means that you're looking for a D that is I, and you can find, or like we want the real part of this log basically to be 1, so that there's no real part. So this is, but the sigmas of the original seed, that's how they show up. You have, if the sigma 2 is 0 in that sector, you don't. But remember that then as soon as you turn on Stokes phenomena, you can go, because then now this analysis is all around, which means that you can easily go to a different region where now you just turned on sigma 2. It's just typically, for example, this is something for the Painlevé 2, you have that if both sigma 1 and sigma 2 are non-zero, you have arrays of zeros here, here, and here. And if n is odd, one of them appears here. If you started with sigma 2 0, you don't have those. But you still have that. But you just need to be a bit more careful about how you define the original trans series. Meaning, I don't know is the short answer. I haven't, meaning I started thinking about actual, again, this problem showed up from really purely orthogonal polynomials point of view, so I didn't think too much about it. And then suddenly I thought, like, no, but what is actually going on? So that's why I said, like, I think that actually one of the things I would really like to understand is what are the zeros? It's but that would define the sigma 1 and sigma 2, right? So once you know what the boundary conditions are, you can still plug it in some sense. You had a question?
Yes, maybe a naive question. If you want it the other way around, so you assign these zeros you find the initial condition, do you recover
so meaning
solutions, or there are some extra ambiguities?
So meaning if you know the two parameters of the zeros, the two parameters of the zeros are mapped to the sigma 1 over sigma 2. They need to be mapped to the sigma 1 over sigma 2. Whether that can be done easily is an open question, because again, you remember that these are asymptotic expansions. Clearly, I'm assuming T is large because I'm assuming X is large. Because they're asymptotic expansions, actually they're pretty accurate to very close to the origin, but they're still asymptotic expansions. I'm still saying I'm looking for meaning very accurate zeros further away from the origin. So the short answer is I don't know. I don't know how to map them. There's definitely a map. Numerically, I've been able to do that for Painlevé 1, for the trunqué solution. But it's numerical. It's not analytic. And meaning you do all the analytic stuff to then do everything numerically. I'm sure that people can do it numerically without all the analytic stuff. So.
What is the final answer for this SDRs? in a sense, what's the relation of all these variables to original variable z? Because there's t, x, z.
And now I might be getting wrong. Is it 3/2 or 2/3? Ugh. Then it's 2/3. I'm sorry. Yep. Yeah, it is. Huh? T is defined by this. This is the definition of T.
So we need to substitute it into the formula for x equals t.
Yep. So this actually, this is just a first approximation. Then you have a whole, the next thing will be something that will be a C1 plus log T C2 with constants. You can find these constants divided by T. And then you have a whole power series of 1 over T to the n with polynomials in log.
So and if we substitute t, then what can we expand or is it just
You're really assuming that basically L really, you can see if you plot these things in terms of in Z, you can see that L labels the position of the zero. The higher the L, the further away from the origin. And basically saying large T is the same as saying large L.
so we can expand the L?
Yes, exactly. That's basically what you're doing. Just because we are starting from an asymptotic series in X, so meaning we are assuming T large. That's. But seriously, it really goes very, again, as any asymptotic series, it's quite good.
And what should be done with M and X? Like, what should be the relation between M, N, and L?
So n equals 3 means so n is the tau n. So it depends now. It labels the. So in Painlevé 2, you had the parameter that is n plus a half. So n is that n. M can be any value from 0 to n minus 1. Right? So, and basically, now I'm slightly confused, but anyway, so basically what you're saying is that depending on the M, you're going to have this the L labels here, but the M labels which array you're in. So M, and you vary, you have to consider all of them. So M, you consider all of them. N is the specific solution that you're looking at.
I think I would suggest that we continue this after the break, and then so let's thank Ines again.